Yes, hello and welcome to another web demo organized by Kissoft AG, where we will cover today complex kinematics in KISSdesign. Yeah. My name is Cengiz Yilmaz. I'm working now more than 10 years at Kissoft AG, and I'm responsible for the system tools, system modules at Kissoft AG regarding the technical support regarding documentation regarding trainings, and we are also in charge of doing engineering for customers using the system modules in Kissoft. And today I would like to talk about a special topic, which is complex kinematics in KISSdesign. I would like to give you some hints about how to solve points where you reach when you build up your models, and these points are some specific situations where you need to have some specific knowledge in the software about how to solve them regarding kinematics when you build your models up. And first of all, I would like to talk about the definition of complex kinematics. Just give you some words like what is really a complex kinematic. It's the definition is different for everyone. Even if I ask at the company, I get different answers from everyone in different departments. So I would just like to show or just give a comment about what I define as a complex kinematics model. Then second point will be about basic principles, kinematical principles in KISSdesign, and how to solve these kinematic situations. And we will talk about multiple boundary models. In the same model, we will also reference the different boundaries to each other. So just to give you to give you the points how to handle these situations. Then I would like to show you how to handle power splits in general. Next point will be about shifting transmissions, and then also epicyclic stages or a general planetary stage, where I would like to focus on the most important points in this specific planetary stage. Yeah. And then in the second part of the web demo, I would like to model the kinematics of a 6-speed automatic transmission gearbox, including the switching matrix, and we would like to shift between the different speeds. Just to show you somehow more or less most of the points will be used in this example kinematic model. So first we go through the principles, and then we use it in an example gearbox. Okay. So let me go through point 1, definition of complex kinematics. If we go to KISSdesign, I have just one cylindrical stage model, which I saved. Will open quickly. Yeah. So the easiest definition, I think, of complex kinematics is everything what's beyond this one-stage gearbox can be defined as complex kinematics. Even if you have multiple stages or multiple boundaries, that's already one step more. So everything what's more than this can be called as complex kinematics in general. This is the most simple case which you can have in KISSdesign with a one input, one output boundary, and in the boundary tab we define the speed and torque values at one of the boundaries, or just one speed and one torque condition, and then the kinematics can be calculated. Yeah, this is just as introduction, a short introduction about the definition. And let me start directly with the multiple boundary model with the basic principles which I was talking about before. I saved the models already in advance, that we don't lose time with the modeling or with the creation of the shafts and adding of the gears. We are really focusing on the specific kinematic points. And the focus of this demonstration of this web demo is purely on the kinematics. in KISSdesign. Yeah. We will not run any strength calculation because we have 1 hour reserved for this specific topic. Okay, so if we have a model or a situation where we have an input shaft and multiple output shafts, or doesn't matter, it can be multiple input shafts, one output shaft, or multiple input, multiple output shafts. We define on each shaft that we want to have some speed or torque defined or calculated a boundary. So this model has 5 boundaries. And in order to run the kinematics, we have to create the gear meshes. So we have to generate the pairs. So this is the first pair, second pair, third, fourth pair. Okay, as we see here. And then the easiest way is, for sure, we have 5 boundaries, so we need to define 5. This model has a kinematical degree of freedom of 5, so we need to give 5 definitions. Let's say we have a speed and torque definition at the input boundary, and 3 additional torques need to be defined. And the easiest is to say, okay, boundary 2, 3, and 4 have a torque defined, and boundary 5 will be calculated according to the definition. So let's say we have 100 Newton meters and 100 RPM. And then if we don't define any other torque going out through the other 3 boundaries, we have the full torque going out on this boundary because we have 1-to-1 ratio everywhere in this example. If we say, okay, since the speed is positive, we need to enter a negative torque here to have an output as well, and the positive torque and positive torque as well. And then we have a remaining 40 Newton meters calculated at the output here. Yeah, or here. Yeah, boundary 5. So this is the easiest way with defining the absolute values for the torques. But there is another additional definition possibility which we have in such cases. If you want to give a relation between the 2 outputs, between the 4 outputs, let's say different outputs, we can say, okay, instead of giving the torque directly, defining the torque directly as a value, I say, okay, the ratio between this boundary and this boundary, and then between here calculating 3 and 4 and these 2, I would like to define, instead of giving a fixed value, I would like to give a certain ratio. And then I say, okay, it's not a torque and speed ratio, it must be a torque ratio for this. And if the torque ratio is 1, we see that, okay, here, since the speed is turned, we need to define a negative torque ratio to have both output power on both sides, because if we leave it like this, it means we have an input here, and 2 outputs, so we have the different torques respectively calculated, but this is not what we want. If we would like to have an equal distribution, then we can go here and say, okay, between these 2 couplings, with these 2 boundaries, I would like to have a -1. Here it's +1 because we have 2 shafts in between, 1 shaft in between. And here again, we want to have negative torque because the speeds are different. The sign of the speeds are different. And then if we check for boundaries, it's automatically calculating the equal torques on each side. Even if I say, okay, here between these 2, I would like to have, let's say, a 0.5 distribution for the torques. It's fulfilling this condition and calculating the rest automatically, that the other condition of having 1 here and 1 speed ratio here is fulfilled, is also calculating these options here accordingly. Yeah. So there is this additional flexibility which I wanted to point out, which can be very convenient to use in such cases. Okay, so with this, the first 2 points we already covered. Multiple boundaries we covered shortly, reference boundaries with coupling connections we also covered. Now I'd like to switch to the power split If I go to projects and open a power split model, yeah, that's also a prepared model where we have an input shaft and an output shaft, two side shafts, and the power should flow through these two side shafts and come together at the output shaft, and then it should go out here. If we don't define a split here, we can try what happens. So first of all, we need to define the meshes between the input gear and one side gear, between this input gear and the other side gear, and then this side gear and the output gear, and side gear and output gear here as well. Okay, so if we calculate only kinematics, first of all, if we check only kinematics, which we can change in the control panel under the calculation settings here. In this situation, let's check how the boundaries are defined. I have one input boundary and one output boundary. In the boundary tabs, I can see that actually, since we have no epicyclic stage here, it's enough to define two, one speed and one torque value. That's correctly defined. And if I calculate now without the definition of a split, it's telling me that the system is kinematically overdefined. So it's not really clear how to distribute the torques between the two paths here. And for this, we need to define a split. We can do that with a right mouse click, going to power flow and power split. And there are two ways of how to define the power split. Either we can click on the element, go to power split window, and use the reference gear. Reference gear is gear 1 here. This is this gear, which is gear 1. And we can define the percentage of the power which should go through this branch in this window, let's say 50%. Okay. The same we could also do if you go to calculation and power split. We have here the same settings, the name of the power split, the mesh, and then the reference gear and input or not, and then the amount of the power in percentage which goes through this mesh. Yeah, so that's already defined. And then now 50% goes here. We still have to define the split on this side to say, okay, we have the same reference gear here, G1. And if the kinematics works well, in this case, the indication in percent of the power flow should be calculated automatically. It should not be an input because it's already defined here to be 50%. The rest will be shown here as 50%. And if I change here, for example, 30%, it will automatically update here to 70. Yeah. So that's a simple model, but in this way, it can be the powers can be defined also in other complex models. If it's a part of a more bigger model, it's always the same handling, and that's the idea of this web demo, to show you the basic principles which you can also use in bigger models. So let's switch back to 50%, and then we have a working kinematic model. As we see, we calculate now, not the report, I want to calculate now, and looks good. Even the boundary, the output speed and the input torque can be calculated this way. Yeah. So that was the power split situation, and just very fast explained how to solve such kind of situations. Let's go to the next one, which is the shifting transmission case. Let's open my predefined model. we have more shafts in this model. It can take a bit time to open. Yeah, now it's opened. What I prepared is we have a simple shifting transmission with one input axis, input shaft, and an output axis with the output shaft and then the gear body shafts, as we see here. And on top of the gear body shafts, we have the different gears. And between the output shaft and the gear body shafts, we used a switchable element, a synchronizer, switchable element, and they are all now switched off. They are not closed. As usual, we always check first the boundary conditions. So we have boundary, input boundary and the output boundary. And we need to define a torque and speed value at the input, let's say, as 100 Newton meters and 100 RPM, the input boundary. Now, depending on which switchable is active, closed, the power flow will be realized and it will go through this gear body and then to the output shaft and will go out from the output boundary. So we can do that manually for sure. We can say, okay, let's close this and then it will go through this. And if we open this and close this one, it will go through these elements. Now, instead of doing that manually, we have a switching matrix. And in order to tell to the software that these are really switching elements to be used in a switching matrix, we have to mark them first. And this can be done in the element editor. So we select the element and we go here to use in switching matrix and click the checkbox for all of these elements because all of them should be used. Okay. And then we can go to calculation, we can go to switching matrix and just size the switching matrix. KISSdesign is automatically now checking for all possible switchables which need to be used in the switching matrix and it's doing the combination with the different switchables, switching them on and off. And this gives us 4 shifts at the moment. And in addition, we need to define the modes. At the moment, it's just mode 1 is defined. So we have to do a combination of these shifts and the modes. We have to click on operating mode and size the respective shifts to be used in the modes. So we have mode 1, gear shift 1, mode 2, gear shift 2, 3, gear shift 3, 4, gear shift 4. Why we need to do that is it can be that we have a second setup here defined, like saying, okay, in another setup, I want to have input torque and input speed at the second boundary, at the output boundary defined as an input. And then we could have more modes for sure. We could like size, and then it will be 4 gear shifts with setup 1 and 4 gear shifts with setup 2. So in total, would have 8 modes in this case. But this is not what I want to do now. So I would like to just use setup 1 for the moment with 4 gear shifts, and setup 2 I would like to delete again. That was just to show you why we need to define the modes. And that's it. Once we have the modes, we can just switch to through the different modes, and we have the different respective ratios if the number of T's are different. Yeah, we will see that also in our example model more in detail. This is just quickly to show you how to solve such kind of situations. Yeah. Okay, so that was this example. Then let's use the planetary gear stage. Okay, so I already prepared the different shafts. We have the sun shaft, the planet group with the gear body and the pin, and the planet ring shaft with the ring gear, and additionally the carrier shaft. As you see here, they are all created using the sketcher. Now, first of all, I would like to create the meshes. So sun, planet, and ring. So without releasing the mouse button, as you see, you can create already the meshes. And it's automatically creating first a 3-gear calculation because we didn't add the planet carrier element to the carrier. So this is just a normal shaft. So if we add, to specify the carrier shaft, we add a carrier element to the carrier. And then once we connect this carrier element to the planet axis, it knows that it's a standard planetary stage, and it converts this calculation to a planetary calculation. Yeah, it would be also possible to create this. I can delete it again just to show you that it can be also created. It can be created before or afterwards. So let's delete. Yeah. So once we add, I do that again. Once we add the planet carrier to the carrier, we connect with the mouse the planet axis, the carrier element, and then if I do it now, it's automatically directly creating the planetary calculation. So it doesn't matter when we click and when we generate the calculation, it's automatically anyway switching to planetary calculation once this carrier element is connected to the planet pin axis or planet group axis. So that's first point, which is important to know. Second point is if we model planet group with a pin shaft and the planet gear body, we need to add a brake element or synchronizer brake element, and we need to close it. It means we need to set the planet pin stationary, so it should not have a rotation. The reason is that in KISSdesign, when we go to the shaft calculation, we operate with the relative speeds in the shaft calculation. So relatively, the pin has no speed, so we have to set it to 0, the speed of the pin, and the gear body will automatically have the relative speed in the shaft calculation, and this will give us the correct bearing lifetime calculation. So it's a different handling than in KISSes. This is important to know that kinematics will work only if the pin shaft is set stationary. Yeah, that's it actually. Regarding the boundaries, so we have sun boundary, ring boundary, and carrier boundary. So we can go and say, okay, on sun, I would like to define speed and torque. And one additional speed is necessary to be defined here in this model because we have 3 boundaries and we have an epicyclic stage, a planetary stage, which comes with an additional degree of freedom for the speed because of the carrier rotation. So it needs 3 definitions, but not 2 torque, 1 speed. Instead, we need 2 speed and 1 torque definitions. And this can be realized with the definition of the speed at the boundary on the ring, for example. Most of the cases set to 0, but depends on the application. Always can also have some speed here. If it's stationary, as mentioned, there is this option with the own input of the speed, and then the output torque and speed values can be calculated. Another way is to say, okay, I don't want to define a boundary here. It's anyway always stationary. Then we can delete the boundary and we can delete the coupling as well and set it stationary using the brake element. And then the kinematics will also work because this is also a definition of speed indirectly of this stage. So it's still 1 torque, 1 speed definition, and the second speed definition comes from this fixation of the ring. So 2 ways to define the boundary or the kinematics. Either we set it stationary using the brakes, or we define the speed over the boundary condition on the ring. Yeah, that's it. These are 3 important points for the planetary stage, and these points are also valid for other epicyclic stages. So, for example, the connection between the carrier and the pin axis, and then the setting the planet pin rotation to 0. These are important points which need to be also used in any kind of planetary application. Even for bevel differentials, it's the same approach, let's say, same philosophy. Okay, that's it regarding the basic examples, basic principles. Now I would like to have this application, what we have seen with this small examples in a bigger example gearbox, in a more complex example gearbox, which is a 6-speed automatic transmission, which I took from the literature. And it has a normal planetary stage here, where the sun is stationary and the input is from the ring. And then there are some clutches which can be active or inactive. For example, here there is clutch A, B, which connects the carrier with the first sun of the revenue set. So that's the second special epicyclic stage which we have in this example, a revenue set with sun, planet, then planet, planet, and planet ring mesh. So the carrier of the first stage is either connected with the first sun here, or it can be connected with the second sun. And then there are 2 breaks. So the second sun can also be stationary depending on the activation of this break at C. And the planet carrier here can also be stationary depending on the activation of the break D. One additional clutch is available between the ring shaft, which is the input shaft, and the carrier, which is mentioned here as connection or clutch E. Yeah. And the output is always from the ring of the revenue set. And this is first of all, we need to understand the kinematics, and then it's important to model it, KISSdesign, and set the different connections correctly. And this is what we will do in the next half an hour. Okay, so let's start from scratch and just start with the sun shaft here. We add the sun gear. Just add directly the brake, let's say, and I call it as fix sun 0. I call this stage as 0. Then we have, as we have seen in one of the examples, we have a standard planetary stage here with a pin and then the gear body. So I start always with a double click, and then with escape I stop the creation of the shaft and set the axis to the same axis like the pin. We have the planet gear and the ring shaft, also coaxial to the sun axis. And this gear is an internal gear here. Okay, so that's the standard planetary stage as known. And what we need to not to forget is, just set this pin directly closed, because this is what we learned before, that the pin shafts must be fixed. So that's fix in 0. Okay. And then here I have my input actually on the ring. I add a boundary. And call it input. Okay. Good. And then I would like to create the next shaft, which will be the carrier shaft. Just to make it short line here. Just a representation here. And then I continue. So the first stage we modeled already with the fix of the sun and the input on the ring. Now we continue with the carrier. And I would like to model this sun first and then this sun shaft. And I would like to connect both the carrier. So there is one connection here. So let's start here. Yeah. A bit more space maybe. Yeah. Okay. So let's say this is my sun. And there will be a connection here between this sun and the carrier, which is connection A. Call it directly connection A. So like this. Yeah, we connect it. And then I continue to model the planet axis here. This is the first planet, which I want to model. Then the second planet. With its axis. Okay. Let's move it to this side maybe. Oh, it's okay. And create the ring shaft as well. The same axis like the sun, and change to internal toothing. Yeah. And we create the second sun here. Maybe I want to start a bit more on this side to be able to connect it with the carrier. This. It has the same axis. This dot is not needed. So we add the sun gear as well. And there is this connection between the second sun and the carrier, which we can see here. That was the first connection A, and the second sun with the carrier is connection B, which I would like to add next. Connection B. It's connected as well with the carrier. And then we need to create the carriers, second carrier as well. And there it's important that we have two breaks in our system. One is connected to this carrier, and this carrier is at the same time also connected to the ring, the first ring. Then the other break needs to be added to connect it with the second sun. Okay. So we need one break to connect with this sun here, and the other break. So let me first create this break, which is here for this sun. Let's say we have it here. And we can also use it as coaxial. And first of all, this is like a housing shaft. First of all, we need to close, and we need to fix it in space. And then, so this is called fix shaft 1. And then we need the connection between the second sun and this break, which is, need to check, which is break C here, this sun C. Okay. Then there is the second break, which is used for to fix this carrier. So we need to first model the carrier here. Okay, coaxial. And then we will have a fixed shaft on top of the carrier. Let's say something like here, which can be also coaxial. And that's also fixed in space, first of all. So that's fix shaft 2. Okay. So this is this fixation here of this carrier, which is D. So we can add here this connection D. This fixation needs to be closed for sure. And then we have a last clutch or connection between the first ring and this carrier here, as mentioned. And that's again this carrier and this ring. So we can just either increase both lengths, doesn't matter. And then I can make this carrier shaft a bit longer. If I start from the left side and come back to the carrier, it will increase my length. And here I can say, okay, this is my switchable or connection E. Yeah. And this can be connected to the ring. Yeah. So what we need to specify is additionally the output coupling of this stage, and then both carriers need to be specified, and all pins should be set, all pin speed should be set to 0. So first of all, I add the output coupling on the ring, and I add a boundary here, yeah, which is my output. And then let's define the carriers. So I know that this is my first carrier shaft. So I say, okay, define my planet carrier as we learned. And we connect this carrier to the planet axis. Here we need to close this pin rotation. And then we have a second carrier where we have 2 planet axes attached. So we have this planet 1 and planet 2 of this revenue set. So we add first this carrier, planet carrier element, and we connect it with the axis, and here with the axis of the first planet group. So both axes need to be connected because they are all they're both elements from the same carrier. Okay, then additionally, not to forget, we need to add these fixations, the pins. Okay, and finally we can create the meshes. So we will create sun planet ring mesh as we have seen before. So let's take the sun, go to the planet, and then go to the ring. Let's try again. Yeah, could be created now, as we see. And then for the revenue set, we have to use pair calculations because we don't have a specific planet calculation for this setup. So we have a sun-planet mesh. Then we have planet-planet mesh. And we have planet ring mesh. And additionally, we have, let's make this a bit bigger, we have a sun-planet mesh with this second sun. Yeah. Okay, we can also rename all of them. So we can say this is sun 1, planet 1. This is planet 1 with planet 2 mesh. This is planet 2 and ring 2. And this one is sun 2 and planet 2 mesh. Yeah. Just to have a certain overview about the used meshes. Okay, that's it actually. Now we need to define in the boundary tab, we need to define the respective input and output conditions. So if we say, okay, we have a given torque and speed value at the input boundary like that, it will not calculate yet the kinematics as we see, because we didn't check the connections here. So if we would manually just say, okay, A and D is active, the others are open. So we go to our switchables, click on A, which is this one. Say, okay, it's closed. And we want to have D closed as well. Right now, all the others are open. So this is the connection between the carrier and Sun 1, and the second carrier should be stationary, so that's why D should be closed. And then we see that the kinematics can be calculated for the first gear. Yeah. Now, for sure, we can do that for all gears manually, but we would use the switching matrix as mentioned in one of the previous example models to switch between the different gears. So let's go to calculation and go to switching matrix and size. Yeah, before we size, if I press now, nothing will happen because we didn't specify which elements should be taken to the switching matrix. So that's why we go to our elements. We say using switching matrix for all A, B, C, D, and E. All of them should be used. Now if you go to switching matrix and size, we see that the automatically system gives us 7 speeds. It's a 6 forward and 1 reverse speed. Either directly we can here switch to reverse. The names can be changed. And as we have seen, A is closed in the first speed and we have D closed, B is open. Yeah, then we have A closed in the second and C is closed, E is open. Third is A closed, B is closed, and the rest is open. Fourth, A is closed, and E is closed. Fifth speed, B is closed, A is open, B is closed, and E is closed as well. Sixth, E and C are closed. A is open, and reverse B is closed, and D is closed. Yeah. So we have A from 1 to 4, E from 4 to 6. Yeah. B is 3, 5, R. C is number 2 and 6. And D is at 1 and the reverse speed. Yeah, active. Exactly. Now, the next thing is, as mentioned before, we need to define this in the modes as well. If I press here, the operating modes definition, we can size, and it's automatically giving me the different modes with the different gear shifts. I don't use a different setup. And here I also change here to reverse. And then, so now we can just switch between the different speeds as we see. And we see the power flow very nicely. We could also activate the sense of rotations, make them a bit bigger. So it's nice to see in mode 1 we have here positive, and in reverse we have negative output speed. That's because of the different gear shifts which are used internally. And for example, we check mode 3. This is the direct mode. This is like the coupled mode because both sun have the same speed. They are both connected with the carrier. And this mode we have the whole system is coupled, and the other modes we have the different respective outputs according to the fixations which are used in the system. Yeah. So that's one thing. Then to see the ratios here, we could go to the boundary tab, and we could reference from output side to the input and check for the value here. Right now we don't have the correct number of T's, so that's why we have just some output speed ratios. From literature, we have certain number of T's in order to reach these given ratios in the presentation. So here I use 31. Here I use 15. Just to quickly show that the ratios are also fitting quite good with the respective number of T's. So we have 31, then 23, 22 here for the second planet. Here we have 41 for this sun, and for the ring we have minus 85. Okay, so and with this we can check again the different ratios. So we have 4.13, which is quite close what we have in the presentation, 2.36, 1.5, 1.14, 0.86, 0.67, and minus 3.1. So they are quite close to what we have in our presentation here as a ratio. So the whole model is defined kinematically very well. In 3D, this would look like for the moment in this way, as we see, because we didn't size the gear stages at all. But I would like to open maybe already a finished model as well here, just to show you how this looks in 3D if we have arranged the gears respectively. Just opening. Yeah, I will switch off the camera shortly because it's slowing down the connection. So if I open the 6-speed with geometry, I just want to show you how this looks like when the gears are positioned and the shafts are somehow arranged. So this is the same model as you see: sun, planet, ring, planet, sun, planet, planet, ring, and then the different connections with to the second sun and so on. And the kinematics work in this way as well, the same boundary definitions. And if you go to 3D now, this would look like this, where we changed the number of planets here under the carrier 1 and carrier 2 here, and we updated. So here I used 3 planets, and here I used sun, planet, 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 and planet ring mesh, and also this second sun planet mesh here. And this chain we have 3 times as well, and we can see that this can be animated accordingly in 3D very nicely as well. Yeah, just to show you that how this would look like in the next steps if we would focus on the positioning of the gears and changing the phase width of the gears and also positioning the shafts. Okay, so that's this one. I would like to close that. Would like to go to our model which we built up together. Now what I want to add also a bevel differential additionally to my gearbox. That's just something which I do to have this additional educational aspect as well. So I will, instead of having the boundary here, I will just delete, and I would like to continue here. And would like to add a bevel stage. So first of all, I add the bevel gear. And then I start here. Yeah, first of all, I need to switch to vertical modeling here. Okay, that's the cage of the bevel differential. And then we can define the 2 output shafts. The same axis. Yeah, like that. And let's add the side gears to these shafts. And then additionally, we also have to add here the bevel gear on the cage, the big wheel. So change the orientation here as well. And then we can switch back to the horizontal modeling, and we model the pin here with its own axis, and we change the orientation here of the planet. Let's make this that. So, okay. Now we can create the meshes first. So here I create the mesh between the bevel, pinion, and the wheel. And then we need to add, this is similar to a planetary stage with a planet sun ring. We can imagine like that. And this is the carrier, which is the cage. The carrier needs to have a planet carrier element. And we need to connect the carrier or the cage with the bevel pin axis. And then we can create the different meshes. So between the bevel planet side gear 1, bevel planet side gear 2, and we add the 2 couplings to the output shafts, and we use the boundary conditions as well. Yeah. Now to define the boundary condition correctly, there are 2 ways. So this system needs one additional speed definition because of this differential, and this additional speed definition can be done either here manually with 0, or if I say, okay, I have like 50, then it's equalizing somehow. Let me see. So this is fine. Yeah, so it looks good. Yeah, so it's okay to have certain negative speed for sure, because otherwise if we give positive, then it's going in from the other side. So that's one thing to define the manual speed. Now instead of defining the manual speed, there is this other way which I mentioned in the first part of our session. Instead of defining here manually and trying to equalize both sides, we can just say, okay, I don't define a boundary here. Instead, I would like to use this option with defining the ratios from one side to the other, saying, okay, we define a speed ratio of 1:1, and it's exactly minus 5.2569 RPM on both sides in this case. And if we go to more realistic values, let's say 3000 RPM, we end up at minus 157.7 RPM in this case. And here, if we check between boundary 2 and input boundary, we see the total ratios. They are multiplied now with the additional ratio which you have here with the bevel stage. Okay, so that was the complete model, including the bevel differential, as you see. Now, where I would like to go through some questions, if we have some, quickly, but no questions arrived. So Don't have many questions. Yeah. I can just come up with one question which came in one of the previous sessions during the web demo, which was about why we need to fix this pin shaft. Yeah, that's a different handling for if you come from KISSdesign, because we are running the calculation in the shafts with the relative speeds now. We come from KISSdesign, and that's why we need to also fix the pin, because relative to the carrier, the pin is not rotating in such a configuration, and that's the reason why we need to fix it now. It's a different approach than from KISSes. Yeah. And there was also another question regarding how to export KISSes models to KISSdesign. And we have a documentation about this, and there will be an additional web demo in October about this topic, and there we will explain this live as well, how to do these steps. Yeah. Okay, so I don't see any further questions, and then with this I would like to really thanks for joining, thanks for attending to our web demo, and please check the additional training options which we have, trainings which we have listed on our homepage at kissoft.com, www.kissoft.com. And yeah, please also check for the further webinars which are coming in the next months. And yeah, thanks again, and see you next time. Bye bye.